alpha of G. This is K3, this is K3, right? So therefore, that's the maximum is if I pick one here, and then I'm not allowed to pick anyone from here. So all I can do is pick one from there. So if I pick these are the maximum vertex I can pick. So therefore, this is equal to 2. So therefore, the minimal number to cover all of the edges is going to be 5. Right? So in this case, you see there's 1, 2, 3, 4, 5. Right? So you need these five vertices to cover all of the edges. Let's look at what is alpha prime and beta prime. Alpha prime is maximum number of the edges. So if I pick this one, they are not adjacent, so I can pick this one, and they are not adjacent. So this one, I pick that one. So I can pick a 3, right? 3 is 1, 2, 3, 4, 5, 6, 7. That's a 7 over 2 low floor. So therefore, this is going to be the maximum one, right? So you are not able to, because this is always less than equal to that quantity. So that's a maximum, and therefore this is equal to 4. Beta prime is equal to 4. That's a minimal number of the edge to cover all of the vertices. Right? Let me give you one quick application problems. So that's these are streets. So these are streets, and the circle are the intersections. Right? So this is my street map, and I want to set up some police stations. So I'm going to put police station at the corner of the streets. Well, my goal is I want to put some police stations at the corner of the streets, right? At the corner of the streets. At the corner of the streets. And what I'm interested in, I want to find what's the minimal number of the police station needed, so that every street is going to be watched, can be watched. Okay, so what I'm interested in is try to find what's the minimum number of the police stations, and you will need, and so that every street is going to be watched, right? Every street is going to be watched. So in other words, is what I'm interested in, if you look at this map, what I'm interested in is corner basically is vertices, right? So you want to find the minimum number of vertices that's going to cover all of the edges. So that's going to be your beta of G, right? What's the number for this beta of G? And let's look at how we are able to find this number. So let me look at what I had here, and so I notice for my graph, I notice a degree of vertex. In this case, I have 2, 2, 2, 2, 3, 3, 3, 3, 3, 3, 2, 3, 2, right? So the maximum is less than or equal to 3. And if I denote this is going to be my x, that's a minimal number. That's a minimal number of the vertices I will need to cover all of the edges, right? And I know the degree is equal to less than equal to 3. So in this case, if I have x many vertex and the total number, total possibility, total number of edges, so is always less than equal to, because for each vertex can have at least at most 3, right? At most 3. So therefore, total number you have x many. Total many is 3x. Is less than equal to 3x, right? So equal to 3x is only if everyone you pick has a vertex has a degree 3, right? But anyway, if this is the minimum number of the coverage is equal to x, the total number can be covered by all of your vertex is always less than equal to 3, right? So let me count how many edges do I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So altogether I have 14. So I should have let me count, double count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then I have 12, 13, 14, yes. So I should have total number of edges, so I should have 14 should less than equal to 3x, so which means x should equal to at least larger than equal to 5, right? So I need at least 5 vertices. So that's at least 5 vertices in order to cover all of the street. So let me try to find whether 5 is possible. Right? So whether 5 is possible. So 5 if only possible is I should make my most of the vertices come from degree 3. So therefore, let me have. This one has degree 3. Right? This one has degree 3. And this one has degree 3. I have 4 of them. So now let me count how many edges I've already covered. Right? So I still have, I will need so I need a 3 is going to be covered. So I need looks like that's this is not good enough. If I pick this one, then this covered, I still have one street is not covered. So I need a different strategy. What if I have 3 of 3? That's 3 of them. 3. So therefore, looks like this is not going to work. So I need. What if I pick this one? Do I have 5 possible? I try to find 5 possible. Of course, if I'm going to have a long street here, then this is 5 is going to be possible, right? So if I modify my problem a little bit, then this 5 is going to be possible. I wonder what happened to my original problem. So let me just sketch my picture here. Try to see whether 5 is possible for this graph. So I have how many police stations I will need. And originally, this plan is I have 4 vertex with degree 3, right? And then plus 1 vertex. Because I only have 1, 2, 3, 4. This 4 vertex has degree 3, right? So this all of them have to be picked. And then if I pick 1, it's unlikely I will be able to cover all of the street. So that's not a good possibility. So what if I have 3 vertex with degree 3 and 2 vertices with degree 2, and then this 9, right? 9 edge plus 9 edge. This is 9 plus 4. That's going to give me 13, right? And therefore, I will not also be able to cover all of my 14th street. So looks like this is also not going to be possible. Okay, so if I look at this graph, what I summarize as let me write it here. So I try to find whether this is going to go, right? So the first possibility is I have 4 vertices with degree, each of them with degree 3, and I have 1 more vertex. Because all of the other vertex with degree 2, right? And the total number of the vertices can be possibly covered is 12 plus 2 is 12 plus 3 is 14. But I only have 4 vertices with degree 3, right? So 1, 2, 3, 4. So all of them have to be picked. And then I look at all of the street. What I covered is I just mark here. Then I need 1 station to cover 1, 2, 3, 1, 2, 3, 3 of them, right? So that's impossible. So therefore, this is a no. Answer is no. You cannot do that. And then what happens if I have 3 vertices with degree 3, and then I have 2 vertices with degree 2. And in this case, I see this is also, again, that's not possible, right? Because now you have 9 edge plus 2 is equal to 13, which is less than 14. You will never be able to cover all of the 14th street, right?
Plus 4.
Plus 4, I'm sorry. Is equal to 13. Will never cover 14th street, right? So this is also not possible. So therefore, which means if you look at it, of course, if you look at 2 vertices and with 2 plus 3 or 1 plus, and all of other case will also be not possible, right? So therefore, x is larger than or equal to 5, and x equal to 5 is not working here, right? So x cannot equal to 5. So therefore, that will force x is equal to 6. Right? So will that be possible? Yes, because now if I just add 1 more police station here, then every street is going to be covered, right? So 1, 2, 3, 4, 5, 6. So this is yes. In this case, beta of g is equal to 6. So in other words, is I will need at least 6 police stations. I will need at least 6 police stations to cover all of that street, right? So that's one of the application problems. maybe let me give one more example. Say I have the following graph. Okay, so I have a following graph. I want to know what is my alpha g, beta g, and alpha prime g, and beta prime g. So this is going to be the edge, ray to the edge. This is going to be ray to the vertices, right? Alpha basically is covering, and beta is going to be independent. So what's the maximum number of the minimum number of the alpha? I'm sorry, alpha is going to be the independent, and the beta is going to be the covering, right? And the sum is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have none vertices, right? Sum should equal to none. So let me look at what's maybe let me start with edges, right? So what's the maximum edge? So this number is always less than or equal to 9 over 2. There's a low floor, and let me look at 1, and then 2. Then I have say 3. Then I have 4 here. So I have the 1, 2, 3, 4, right? So they are independent. They are independent edge. So therefore, this is less than or equal to, that's a maximum number you can obtain, right? So therefore, this is equal to 4. So therefore, this is equal to 5. So the minimal number to cover all of the vertices, right? Minimal number of edge to cover all of the vertices is equal to 5. And let me look at what is alpha and beta here. Beta you can look at, that's a minimal number to cover. If I say something inconsistent, that's alpha. Yeah, should be. Alpha should be the I'm sorry. I think this should be independent. So that's 4. This is 5. So that's alpha is independent. Beta is covering. Yeah. What I said is right. This is the independent. This is the covering, right? So now let's look at how many independent. What's maximal independent vertices I have here. So if I have 1 here, then this is 2. There's no edge, and this is 3. This is 4. So I have 4 of them, right? So there's no, they are not adjacent. They are not adjacent. So that's 4 again. And this is always less than or equal to they are not adjacent, yeah. So therefore this is equal to 5. So because the sum is equal to 9, right? Okay, so you can think a little bit more about that, and we'll figure out, compute the number according to this graphs. Okay, basically this is what I planned for today. So today basically we studied all of the four numbers for the graph, right? Alpha G, beta of G, and then alpha prime G, and beta prime G. So this is this will corresponding to the edges. This corresponding to the vertices, and beta alpha is going to be corresponding to the independent. Independent, in other words, is non-adjacent. Right? So you are not supposed to have adjacent here, right? So they are non-adjacent. Beta is going to corresponding to covering. So when you have a covering edge, so that means cover all of the vertices, right? When you have a covering vertices, so which means cover all of the edges, right? So that's a covering. So this is the minimal number of the covering. This is the maximum number of the independent set. So they are all related to each other. I know the sum is going to equal to the order of the graph. The sum is equal to the order of the graph, right? So that's this one is a little bit kind of more interesting to us because this is what we call the matching, right? And the beta prime, beta of G, sometimes minimal number of the vertices that's going to cover edge. So we do also have a few applications in using this constant, right? Okay, so basically that's all for today's lecture. Thank you. Yeah.